In this lecture, we're going to talk about formulation tricks, and along the way, we're going to extend our ideas of formulations just a little bit. First thing we'd like to do is devise some formulation trick that's going to model disjunctions, and specifically disjunctions of constraints. So let's suppose we have some variable x, and x is going to be some real number between 0 and some upper bound u. U is for upper bound. And we'd like x to satisfy either one or another constraint. The first constraint is a1x is less than or equal to b1. The second constraint is that a2x is less than or equal to b2. We're going to model this disjunction of constraints as an integer program, or rather extend this disjunction of constraints to be modeled as an integer program. Before we start modeling it, we're going to have to define some value, capital M. And M is going to be the maximum value of a1x minus b1 or a2x minus b2 over all values of x. So x between 0 and our upper bound u. That is, M is going to be the maximum difference that we can possibly achieve over all values of x between one or the other of these constraints. So to model this disjunction as an integer program, we're going to write our variable x. And x is going to take the same range of values. It's going to be between 0 and our upper bound u. We're also going to invent two new variables, y1 and y2. And y1 and y2 are going to be binary variables. That is, they're going to take values of either 0 or 1. And then we're going to write our constraints, except we're going to write our constraints as a difference. So I'll have a1x minus b1, and we're going to say that this is less than or equal to m. Remember, m is an input parameter, this large number, multiplied by 1 minus y1. We're also going to have a constraint a2x minus b2 is less than or equal to capital M times 1 minus y2. We'll have that y1 plus y2 is equal to 1. The idea here is that y1 and y2 are going to indicate which constraint is on. So if y1 is equal to 1, then our first constraint is going to be on, and x is going to have to satisfy it. Conversely, if y2 is equal to 1, then our second constraint is on, and our variable x is going to have to satisfy it. And we can see from this third constraint that one or the other of our constraints is going to be on. We can make this a little bit more precise. Let's suppose that y1 is equal to 1. That is, our first constraint should be interpreted as being on. If y1 is equal to 1, then we look at our top constraint, and we see that a1x minus b1 is equal to 0, which implies that a1x is less than or equal to b1. And here, let's change this back to a less than or equal to. That is, if y1 is equal to 1, then a1x is less than or equal to b1, which means that our first constraint over here in our disjunction is actually activated. Conversely, if y1 is equal to 1, then we get that a2x minus b2 is less than or equal to m. But this constraint is always going to be true. The reason why is m is this huge number. M is going to be the max over all values of x of the largest difference this constraint can take. Because m is this largest difference, our difference has to be less than or equal to m at all times for all values of x. So when y1 is equal to 1, the second constraint isn't active. If we did the same reasoning for y2 equal to 1, we would get a similar set of points and reason that when y2 is equal to 1, the second constraint is active. So we've properly modeled this disjunction. We have our variable x, and we've introduced this variable y1 and y2 that indicate which of our constraints is going to be active. Now let's look at another modeling trick, or another formulation trick. How can we model or formulate maximums in our program? Specifically, we're going to minimize some variable y, and y is going to be equal to the max of x1 or x2. x1 and x2 have to satisfy some constraint, and for simplicity, we've only put one constraint, x1 and x2 can satisfy any number of constraints in reality. Just to make this an integer program, we've said that y is greater than, or y is in the set of natural numbers. Y can really be anything. It could be in the real numbers, or it can be binary. x1 and x2 are going to be any two real numbers. What we'd like to do is we'd like to take this program that we've written, which is not linear because it has a maximum in it, and get rid of the maximum. The way we're going to do this is sort of the obvious way. We're going to keep the objective the same, that is y is going to be minimized. And now instead of y being equal to a max, y is going to be greater than or equal to x1, and y is going to be greater than or equal to x2. The other constraints are going to be the same. a1 x1 plus a2 x2 is going to be greater than or equal to b. The other constraints for y and x's, we're not going to write them. One thing that we should notice now is this is a trick. You may have seen it in linear programs, but it doesn't exactly get us a formulation. Unfortunately, this is not a formulation. And this is an important point. Specifically, this isn't a formulation because we can have feasible solutions that could never really map to the previous feasible solutions. For example, here we can have x1 equal to 1, x2 equal to 1, and y equal to some huge number like 1,000. This is feasible in our integer program, or our linear program. However, x1 equal to 1, x2 equal to 1, y equal to 1,000 is not feasible in our original solution, or our original problem. The reason why is because y has to be equal to the maximum. Over here, we've relaxed that. Y is only going to be greater than or equal to x1 or x2. So in a strict sense, this trick that we've used doesn't actually give us a proper formulation. But really, this trick that we used is going to be good enough. It's going to be good enough. And the reason it's going to be good enough is because x1 equal to 1, x2 equal to 1, and y equal to 1,000 is feasible, but it's not optimal. And if we looked at any optimal solution to this program, our newly invented program, any optimal solution is going to map to any optimal solution in our original problem. So this good enough sense is that not that every feasible solution is going to map to another feasible solution, but optimal solutions are going to map to optimal solutions. So let's make this idea more precise of having a solution or a formulation that's good enough. We'll call this a formulation in the weak sense. In our original definition of formulation, we have to have that our set X of lattice points, or whatever feasible points, has to be equal to the intersection of our polytope with this set of lattice points and real numbers, this continuum. Our weak sense is going to be different because instead of mapping feasible points to feasible points, as our true definition does, our weak sense is going to map optimal solutions to optimal solutions. So now we're going to take any optimal solution in our feasible region X, and that is going to map to any optimal solution in our region defined by our polytope intersected with our lattice points and real numbers. This is a formulation in the weak sense. And to be precise, when I've written opt X here, this is going to be the set of optimal solutions in our set X. And similarly for the other optimum. So this formulation in the weak sense is mapping optimal solutions to optimal solutions instead of feasible solutions to feasible solutions. This is going to be powerful as we continue to develop formulations for combinatorial problems.